Welcome to this video in which we introduce the idea of a truss and we talk about how to do a static equilibrium analysis of trusses and the members in trusses. So on the screen we have a picture of a bridge, a truss bridge, and the idea is that we actually have in a sense two trusses. We have the one on this side and then the one in the back. Trusses, at least bridge trusses like this, are typically designed to carry loads in a plane. So this truss is designed primarily to carry vertical loads in this plane. And then we've got another truss on the other side. They're connected together. The roadway is connected to the joints, and it holds the car up. Trusses have received a lot of use. They are strong. They're typically rigid. And they make efficient use of the material that they're made out of. And so, particularly in the late 1800s and the 1900s, you saw an awful lot of large bridges being made out of trusses. Today, that's somewhat less so because we're getting better at doing interesting things with concrete. So anyway, this is a truss bridge. We're going to begin by analyzing a somewhat less complicated truss. So this is the truss bridge that we're going to analyze, and in fact it probably would be a good idea just to make sure it's clear what the members of this truss are. We have this guy here, this guy here, this guy here, and this guy here, plus one more, this guy here. Oops, that's a not very well drawn one. Okay, this guy here. Okay, and we will do a two-dimensional analysis, and in fact, for almost all the truss problems we work, we'll assume two dimensions. Again, because many trusses are designed to pretty much carry loads in a plane. There are examples of three-dimensional trusses. For example, the International Space Station. Several of the large booms on the International Space Station are actually three-dimensional trusses. Okay, so but we'll stick to two-dimensional analysis for most of this. Okay, so the first thing we need to do when we look at a truss structure that we're going to analyze is we need to figure out how it's going to be supported. And the assumptions that we're going to make here may not make any sense to you because they seem kind of weird. But the idea is we'll assume that on one side of the bridge, in this case over here, we have a support that basically connects the two truss members, or to the truss members, but it's rotational support. It allows them to rotate in these directions. Okay. Now, again, this is not real life, but this is necessary to make the analysis easy. Another assumption we'll make, and this will seem even more bizarre, is over on the other side, we have a support that is on rollers. And so you're thinking to yourself, okay, I've rarely seen a bridge where one side is hinged and the other side is on rollers. The exception to that is if you're designing things for thermal expansion. This is kind of what you do. This isn't necessarily exactly what you do. The reason for doing it this way is we'll have a reaction force in the X and Y direction here. We'll have a reaction force just in the Y direction here. And it turns out without that sort of assumption that one side is on rollers, if we had another reaction force here, then it would actually not be possible to determine what these two reaction forces are. We would just know that they would sum to zero. And so that's why we end up making these assumptions. It's necessary for what's called a statically determinant problem, where all the unknowns can be solved for. Okay, and then each of the members of the truss, again, each of these bars like this, this, and this are members. We'll ignore some of the other things that are going on here. It looks like there's sort of a safety railing, and we've got some stuff going on out here coming out the z-axis. That's to keep the truss parts standing upright and so on. We'll ignore that. Okay, so we're going to assume that these members are weightless. And you're saying to yourself, wait, steel is not light and fluffy. But the assumption that you typically make when you're analyzing a truss, at least for the first approximation, is that the weight of the members is small relative to the weight that the truss is designed to carry. And so we will assume that these members are completely weightless, and we assume that these joints are pinned with frictionless pins. In other words, the members are free to rotate. Say this member here can rotate either this direction or this direction at this joint, and it's a frictionless rotation, so the joints don't apply any torque, and they don't basically set any constraints on the angle at which the members can come into the joint. The reason we do this is because if we have a member here, let's just draw this guy. We have a pin here and a pin here. This becomes a two-force element. And two-force elements are handy because what it means, if there's only two forces and I have static equilibrium, then the forces acting on each end of the element have to be the same magnitude. So I can say that I might have a tension in a member TAB. At that side, well, I'll have that same tension in the opposite direction on this side. And we know that these forces have to act in the line of the member. Okay. Now, unlike a rope, where ropes can only pull on things, if you try to push on things with ropes, it doesn't work very well. These members are rigid, and so this tension may actually be as I've drawn it. Well, in this case, it looks like I've drawn it so that the member may actually be pushing against something else, or it may be pulling on that something. Okay, and so our goal is to find the tension in all of the members. The reason we need to do this is we need to make sure that our design is such that we have the proper strength materials that will be able to handle the tensions, the tension and compression that are part of being this truss. And so our goal now is to solve for the tensions in all of the members. So that's the introduction. Let's go ahead and get started on actually solving the problem. Okay, the way we'll do this is we will build a free body diagram or draw a free body diagram of the entire structure and the support reactions and the loads. In fact, I haven't said anything, but let's suppose for the sake of analysis that I've got a load here of 8,000 pounds. Okay, so rather than the bridge being empty as you see it here, there's like a really big truck sitting on the bridge right in the middle of it. Okay, and so what we'll do is we'll start off with the free body diagram of the entire bridge, the reaction forces here and the load, and this will allow us to determine what these reaction forces are. And then the way we do the analysis of the tension in each member is we'll actually draw free body diagrams of these pins, of the pins that connect the members. So we're essentially drawing free body diagrams of points in space, with the idea that, and since they're points, we don't have to worry about moments at each of the pins, but we will have to make sure all of the forces are balanced to have static equilibrium. Okay, so hopefully this makes sense. Let's go ahead and start the analysis. Okay, so the first thing I need to do is draw a free body diagram of the entire structure. So I'll just whip out a free body diagram here. Okay, there's our free body diagram. We are going to have a load, and again, we've said that the load is going to be 8,000 pounds. And we're going to have reaction forces. We'll have a force that I've called here FAY, and a force that I've called here FAX. This is from the pinned side of the bridge. And then we'll have another force, let's see, we'll call this, why don't we call this point, in my notes I call it C, so I'll call this FCY. And we'll actually label these points. We'll label this point A, B, C, and D. Okay, so this is our free body diagram of the entire structure. And we need to analyze it then to see what these forces are, FAX, FAY, and FCY. We have three unknowns, and fortunately for a two-dimensional body in static equilibrium, we can solve for up to three unknowns. So first, let's say the sum of forces in the x direction is equal to 0. Well, FAX is the only force in the x direction, so that force is equal to 0. Okay. Next, let's say the sum of moments about point A is equal to 0. And the reason I'm choosing point A is because two forces go through point A. If I choose point A about which to compute my moment, I don't have to worry about FAX or FAY. And I didn't draw in dimensions. I'm just being lazy all around here. Let's assume that this is 10 feet, and that this is 10 feet, and this is 5 feet, which means that this angle here will be 26.6 degrees, as will this angle. Okay, so computing moments about A, well, this 8,000 pound, we'll do this guy in light blue, this 8,000 pound weight is going to have a moment arm of 10 feet about A. So I've got 8,000 pounds times 10 feet. And that is negative because it's clockwise, plus FCY is going to have a moment arm of 20 feet, and this has to be equal to 0. And so I can solve this for FCY, and I'll find that FCY is equal to 4,000 pounds. And finally, let's see, the sum of forces in the y direction is equal to 0. Well, I have FAY minus 8,000 plus FCY is equal to 0. I know FCY is 4,000 pounds, and from this then I can easily solve for FAY to be 4,000 pounds, which is what you would expect if I have a load right in the middle of the bridge, and the bridge itself is symmetrical. Then you would expect the reaction forces on both sides to be symmetrical. So each side of the bridge is supported by half the load. Okay, so I'm out of time on this part. In the second part, we will now find free body diagrams of each of the pins and use those free body diagrams to solve for the tensions in each of the members of the structure. So stay tuned.